All right, inverse functions and derivatives. Let's talk first about slopes of lines. So in this particular line, the function, all the tangent slopes are positive. They would be uphill left to right. Therefore, this graph is what we call strictly increasing. On this side, all the tangent slopes would be negative, in this case, strictly decreasing. In the last case here, they both increase and decrease, and this graph would not pass what's called the horizontal line test. If I drew a horizontal line, it would hit the graph in 2 or more points. So a function has an inverse if and only if it is monotonic. And by monotonic, we means it strictly increases or it strictly decreases. One of the two, not both. H of x is not monotone, therefore it does not have an inverse. Okay? You can check a function to see if it's monotonic by using the first derivative test. So remember that another name for tangent slopes is derivative. So if all the derivatives are positive, that's a strictly increasing function. If all the derivatives would be negative, that's a strictly decreasing function, therefore monotonic, therefore inverse exists. So let's go take a look at an example. So if we had a function f of x equals 1/3 x cubed plus 2, notice that the derivative is just x squared. Well, there is one critical point at x equals 0. However, on both sides of that, f of negative, when f prime of negative 1 is greater than 0, and f prime of 1 is greater than 0. Therefore, it increases, it hits 0 once and then increases again. So again, it is strictly increasing. It does 0 out at one point, but for the most part, this dude is strictly increasing around. So it is monotonic, and yes, an inverse exists. How do we find an inverse? So first of all, we write the thing in terms of y. Then we swap the x and y values, we solve for y, and this is called f negative 1 of x, and this is called f inverse. Okay, so an example would be over here to the left. Start with f of x equals 1 minus x cubed. Put it in terms of y. Y equals 1 minus x cubed. Swap x and y around, and then solve for this y over here. In this particular case, all I did was subtract x from both sides and add y to both sides. Y cubed is 1 minus x, cube root of both sides is y is equal to cube root of 1 minus x. Therefore, I can switch back to inverse notation. F inverse of x is equal to the cube root of 1 minus x. What are some properties? If I take a composite function of f of its inverse, I get the identity function x. I get y equals x. So anytime you take a composite of a function and its inverse, you should wind up with x as a result. If f of x, the function, contains a point AB, then its inverse contains the point BA. And this property here will kind of lead to the last property, that these graphs are symmetric to the line y equals x. So that y equals x, that one sloped line that runs all the way through the origin and up like this, the graphs will make mirror images around that y equal x lines. Let's go a little farther. This is actually a little more interesting. If f of x does have an inverse, call it f inverse of x, then f inverse prime of x is equal to, and they give you this formula here, it's 1 over f prime composited with f inverse of the actual number x. And this is a little more interesting, but let's take a moment or two and take a look at it. So first of all, we're going to show that this function is monotonic and therefore an f inverse of x exists. So we take the derivative and we find out the derivative is x squared plus 1, and this function has no critical points and it is positive for any x that I plug in it. So it's definitely monotonic, so an inverse exists. All right. If I tried to solve this, you'd find out that you'd have x equals 1/3 y cubed plus y, and you'd be like, I have no idea how to solve this thing for y once I plugged it back in. So we need a shortcut, and in this case here is the shortcut right here. So with this shortcut, what we're going to do is we're going to find f inverse prime of 12. And how are we going to do that? First of all, we're going to find the formula, and we're going to say f inverse prime at 12 is equal to 1 over f prime, and then composited with f inverse of 12. So how do we start with the most inside point? So how do we figure out what f inverse of 12 is? Remember, this is the part where if the inverse maps a to b, then the original function must map b to a. So we swap these over and say the original function. We set the original function equal to 12, and without too much mathematics, we can find out that that had to be the point the original function had the point 312, which basically means the inverse has the function 12, 3 on it. So f inverse of 12 is equal to 3. So we can plug this in down here. So f inverse of 12 is equal to 3. So now we just have to find f prime of 3. And when we do that, we just pop back up here to the prime function here, which is just x squared plus 1. And we say that is 3 squared plus 1, which is 1 over 10. All right, that's enough for today, and we will hit this again tomorrow. Thanks.